Well, hello, fabulous students. I would like to take a look at some more volume information. In fact, I want to start with this thing called volumes. It's time to be clear about these. Okay. My recommendation is that if you haven't done this worksheet yet, you stop the video and you go do it. No, really. Stop the video. Go do this. This is definitely something that you need to get comfortable with, and the only way to get comfortable with it is to do it. And then we'll just sort of quick talk through it. Okay? All right. Well, welcome back. Hopefully you listened to my advice. Often people who do find that they are really grateful for having done that. So, our worksheet says, number one, when this region, oh, and by the way, this is y equals sine x, and we have boundaries of x equals pi over 2 and y equals 0. So what does our region look like? Boink, boink, boink. This is our region. It's bounded by sine x, it's bounded by y equals 0, and it's bounded by x equals pi over 2. Okay, when this region is spun around the y-axis with washers, would this be a dx or a dy integral? Okay, so I'm rotating about the y-axis. And if I'm using washers, I'm drawing something that's perpendicular to the axis of rotation. And so what would I see here? Well, I see washers in this situation is going to be dy, because the thickness of that washer would be measured here on that y-axis, which I guess means shells will be dx. But don't take my word for it. Let's actually look at that picture. So I'm doing shells. This is my axis of rotation. I draw something parallel to that axis. And at each end, I draw a circle whose center is the axis of rotation. Now the thickness of this shell is measured along the x-axis. So yes, that's a dx integral. Okay. Next, when the region is spun around the x-axis. Okay, well, let's spin this region around the x-axis. Sine region around the x-axis. With washers, I draw something perpendicular to the x-axis. And there's my circle. And this is going to be some sort of nose cone bullet kind of shape. And in this situation, I have circular discs, and these discs have a thickness that is measured on the x-axis. So problem 3, dx. Now for problem 4, with shells. Okay, well, with shells, we're talking about drawing something parallel to the axis of rotation and drawing a circle at each end. Well, the thickness of those layers, this thickness, is measured here. So that's a dy. So a dx washer is going to be a dy shell. A dx shell is going to be a dy washer. Okay. 5. What if we go around x equals pi over 2? Okay. So here's pi over 2. And we're rotating about this axis, this region. With washers and discs, I'm going to draw that segment that's perpendicular to the axis of rotation. And since my region lies on that line, I expect to get a disc here. It is a dy thickness there. That's a change in y values I see there. So for problem number 5, we're saying that disks will be dy, and 6 if we do this with shells. Okay, here. And we're rotating with shells, so I draw something parallel to the axis of rotation. And there's my shell. And the thickness of that layer is measured there across the x-axis. 7, spun around y equals 1. Okay. Here's y equals 1. It's true that the region intersects y equals 1, but we need no gap between the region and that axis of rotation. Since we have a gap, when I draw my segment that's perpendicular to the axis of rotation, I see that I'm going to have circular disks, and the thickness of those circular disks is going to be measured here along the x-axis. So 7 is a dx. And what about 8? Do this with shells. Okay, so going to rotate about this axis. And this is y equals 1. Because I'm doing shells, I draw something that's parallel to the axis of rotation and draw circles at either end of that segment that I drew. The thickness of these shells, see it there? That's going to be measured here. That's a dy shell. Okay, and our last two, now we're spinning around 3 pi over 4. So our region looks like this, and here's this axis of rotation. Okay, well, with a disk or a washer, when I draw that segment perpendicular to the axis of rotation, I notice that. But I notice here also, look, inner radius is not changing. Inner radius is the same for any of these little r's. Okay, so there's my little r. And then this generates big R. The thickness of that shell is measured along the y-axis. I'm sorry, the thickness of that washer is a dy washer. And what about the last one? Shells. Okay. Going around 3 pi over 4, we have this region here, stops at pi over 2, and now I want something that rotates around this axis. It's a shell. So something parallel to the axis, and then there we go. And the thickness of this is going to be measured on the x-axis. Fabulous. Okay, so next we're supposed to, and I know I just drew them, but I'm going to draw them again. Now we're supposed to not only sketch, but also label what big R and little r would be, or what R and H are going to be. And so let's go back to this first one. And the region is spun around the y-axis with washers. So there's our region. And we're taking this region and we're spinning around the y-axis. Well, this is little r. And I notice that little r is changing. Little r is curiously that distance to that ordered pair called xy. So I think little r is x. Good. And then what about big R? Well, big R goes from here to here. Always, right? I mean, big R is always this lining up here. So I think big R is pi over 2. Now, remember how we said that this was going to be a dy integral? We would measure that thickness on the y-axis. It means I don't want an x here. It means I want a y. So let's see what we remember. This is sine x And I'd like to solve this equation so it says x equals. To do that, I need to take the inverse sine of both sides. And so I end up with inverse sine of y equals x. So radius equals x can become inverse sine of y. And my integral? Sure. We're integrating from, and these are y values, right? So we're going from here to here, not here to here. In our shape, this is our highest y value, and this is our lowest y value. We're going from 0 to 1. And our little r is inverse sine of y, and our big R, we said, was a constant pi over 2. However, remember our formula is big R squared minus little r squared. So I actually need to square that, and I need to square that and put a minus between, and don't drop the pi. Okay, so we didn't have to actually set this up. All we needed to do was claim little r and big R. All right. Next, what are we rotating around next? Oh no, we're doing the same rotation, but this time we're doing it with shells. Okay, so here's my region. I'm doing shells. The shells look like this. All right, so what can you say? Well, this point is called xy. And I know that this distance is y, and this distance, in addition to being the radius, is x. Since this is a dx shell, I want everything in terms of x's. Looks like radius, no problem. But what about height? Well, we identified the height of this cylinder as being our y value. And remember, our function here is y equals sine of x. Sine of x, yes. Okay, so my integral would be 2 pi x times sine x dx. And because I have a dx integral, I need x values. The last problem we needed y values, but here we're integrating from 0 to pi over 2. Okay, nice setup. Let's move on. Number 3. Number 3 says we're going about the x-axis this time. Okay, first with disks and washers. Oop. Because our region fully lines on that axis of rotation, I know that my radius of this circle is just the y value here. And since this is a dx slice, I need to turn that into x's. Luckily, I know this curve is called y equals sine x. So r is sine x. And I guess if I were integrating, I'd want pi r squared dx. And so I'm going to have pi sine x squared dx. And we're integrating x's, so we're going from here to here. 0 to pi over 2. And yes, I would pull that out. And yes, I would use my power reducing identity here. Because otherwise it's going to be really hard. Okay, that was disks. Now let's take a look at rotating around the x-axis, but this time with shells. And when we do shells, we need to find a radius, and we need to find a height. We already know that this is a dy thickness, and because of that, I want r and h not to have any x's, but just to have y stuff. So let's see what we can notice. If there's an ordered pair here called xy, this distance is our y value. Well, that's also the radius of this shell. Now the height is this, but you know, if I drew this cylinder up here, like my radius, my height changed. So, how can we describe this height? Well, I think right minus left is the best approach for that. So the right is this vertical line, pi over 2. And the left, though, the left is not x. This is x. This is pi over 2, which means my height must be pi over 2 minus x. Okay. Isn't that interesting? It's just going to be x. And what's x equal to? X equals sine x. We do the inverse sine of both sides. Get that x equals inverse sine of y. Okay, so our integral is going to be 2 pi y sine inverse of y dy. And we're integrating y's, so we're going from 0 to 1. Okay. What's next? I think that was just, yeah, okay. 5, we're spinning around, x equals pi over 2. Okay, here's my axis of rotation. When I think about doing this with disks or washers, I notice that this distance is x, and this distance is not x. This is pi over 2. This is x. So my radius is going to be pi over 2 minus x. Oh, but wait a second. This is a dy slice. So pi over 2 minus sine inverse of y. There's my little radius. Oh, that's fabulous. So my integral pi over 2 minus sine inverse of y squared dy. And we're integrating from here to here. So 0 to 1. No freaking way am I doing this without a calculator. I mean, baby, don't be crazy like that. Okay, so can we do the shell version? So here we go. Shells. Okay, well, I notice again that this is x, and this is pi over 2, and that's my radius. It's kind of interesting to get the radius the same with both. So my radius here is pi over 2 minus x. Aha! This time the thickness is dx. So I don't actually have to change this x into sine inverse y. Well, that's handy. Now what about big R? Well, big R comes from big R. No, I mean h. Sorry. H. H is this. Well, at the ordered pair xy here, that's x, and this is y. So our height is our y value. Since this is a dx integral, I need to get rid of y and replace with sine x. So I have 2 pi sine x times pi over 2 minus x dx. And since I'm integrating x's, I'm going from 0 to pi over 2. Okay. What about rotating about y equals 1? There's my region. Here's y equals 1. Well, if I draw something perpendicular to that axis, I see that I've got a little r and a big R. Now, this big R, no matter where I draw that segment, like I can see that the little radius is getting bigger as I head this way, or smaller as I head that way. But big R staying the same. Big R is 1 minus 0. High minus low, 1. What about little r? Well, let's get rid of some of this visual noise and take a look at explicitly finding little r. So I draw that segment perpendicular, and I can see here little r. I know this is y, and I know that this is 1, and so little r is going to be 1 minus y. Big R was a constant 1. But this shape is a dx integral. Dx integral. And because this is a dx integral, I want 1 minus sine x. So my setup, dx big R squared minus little r squared, and we're going from 0 to pi over 2. Okay. What if we do about y equals 1, but this time with shells?